Okay, today is June 22nd, and I'm here at Searl Magnetics with Jason Pt1, and we're just going over some pretty cool things with Searl Magnetics. He's about ready to show me his generator.
Well, this is not a generator. What this is a homopolar motor. This is a demonstration unit to show the characteristics of what the prototype, how it would function. This is just to give an idea of the motorability, of the magnetic interactions. You see everything stays on point, everything remains equidistant automatically. It's part of the function of the inherent design. Everything just automatically stays on track. Cool. This is a power supply, so this is being fed about 5 volts at 1 amp.
Perfect.
And yeah, a lot of people think that this is producing power. Nope, this is just a homopolar motor demonstrator. And let's just turn this guy on. It's on. Wow, it's not doing anything. Why? Because you haven't added any force to it. Add a little bit. Now you give it some direction. Now it'll maintain that. I'll bump it up a little bit there. It's at 5 volts. Now it's about 6 volts. And at a constant load, it will spin at a constant rate. Okay, so the point is to show that electricity is flowing through this gap. Whether the electricity is coming from a power supply, from the coils to the core, or whether it's coming from the prototype, from the core being delivered to the coils, there's electricity flowing through this gap. Regardless of which direction it's going, it makes the magnet spin. Electricity goes this way, magnets go that way. So that means the magnetic must be aligned axially. So you have the 3-finger motion. Magnetic, electric, motion. Okay, everything's proved true there. So this is indeed a functional design as a motor generator. That's what this is to prove. Now, Professor Searl says that at a sufficient speed, these will lift off of the stator ring and become frictionless bearings. But you can obviously hear, you know, there's friction here. They're touching the surface. They're rolling around on their axis as they orbit because they're touching the surface. So how could they spin on their axis if they weren't touching the surface?
Interesting.
They wouldn't. They would only levitate. And that's what Fernando Morris, when he first, well, I built these with him the second time. He had an original mock-up. The first time he did that, he would little locomotive there. First time he, put, this is just a standard neodymium magnet. This is just a copper ring, solid copper ring spinning. When he put the magnet originally over the copper ring, it would levitate, but it wouldn't spin. And here with your hand, just do this and then approach that with that. You can feel, the diamagnetic repulsion.
Oh yeah, it has a force to it.
It's a diamagnet, copper and a magnet. So when it's in motion, you can feel it's like resistance, like underwater or something. Okay.
Sort of like the when you drop a neodymium magnet through a copper tube.
Copper tube, but this is, instead of it going through a copper tube, what happens if you rotate the tube and you have a magnet on the outside? Same thing, you get the repulsion effect. Also, if you have a copper rod and you have a magnet ring around it, spin the copper rod, the magnet ring will stabilize around it, like a shaft without a bearing. It just becomes a frictionless bearing. So that's just to show, okay, there's a repulsion factor, but it's not spinning. But this, now if you look underneath, it's not touching and it's spinning. Okay, wait a minute, that's something different. If we had one of those magnetic viewing films, which I don't have, it's in the other room, but for the sake of the camera, I don't want to run away. If you were to put this over here, you'd see, like a serpent's tail waving, which I have on another video, to show that the block wall is wavering. And without that waver, you would not get the spin. So when Professor Searl says he imprints this waveform onto these materials and onto this. When those waveforms are imprinted and then it's in motion, then the eddy currents take effect and you get this spin with the levitation. Otherwise, without the waveforms, it wouldn't do anything.
Is there something inside of here?
There is. There is a regular magnet at a 45-degree angle to simulate a wave. So as you spin it, it tumbles and creates
Got it.
a wave. But without that, wobbling motion, you don't get the spin. So how do you imprint that wave or something onto the materials? That's what this little demonstration is for. Let me turn on the... What you have here is a analog Gauss meter to a digital oscilloscope, and what we have here is our little magnet ring that Fernando Morris uniquely magnetized. And this is just like a little dynamo, just like a smog check on your tire, just to make it spin. And what we could see here on the oscilloscope is this varying waveform. So as it spins, it creates a wave. And the trick is to try to get that really smooth into a really smooth sine wave, so that when these are spinning, all of these individual parts are acting like a planetary gear around the larger stator, which is also magnetized uniquely. And it would look like that. That in the center is nickel, because if you have regular neodymium in the center, it tends to oxidize and turn into a powder like that. And, yeah, just like that. Semi-toxic powder. So.
Okay, so don't die until we're done.
Right.
So neodymium powders out
very quickly. And that's evidence that it gives off its energy because it's oxidized.
The things that I've noticed from powdering metals is that you're producing some sort of a gravitational wave. You're producing a different energy than you would be from a DC or an AC circuit, which would be, for this conversation, I'm not saying this is, but towards a linear magnetism, which is more of a gravitational wave. If this thing is powdering off the neodymium, then it's being pulled apart.
Yeah, in the normal air. But once the device, everything's magnetized and everything's put together correctly and to specs, everything's made to the proper densities, and then it's in motion, it doesn't oxidize because it creates sort of this vacuum effect, and there's a surplus of electrons. I hate that term. I'm not particular to the electron theory, but a lot of people are, so we'll just talk with it. So it says that there is like it's an electron emitter from the equator in this dual toroidal circuit. So it's coming in the top, it's coming in the bottom, and out ramjetted out the equator. And because there's so much surplus of electrons, it's negatively charged, and because of the intense electrostatic field, it creates a vacuum. If you have like a Van de Graaff generator, that's a 500,000 volt generator. When that thing pops, you can feel the air move around. So if you imagine you have a sustained, really high voltage unit, you're going to get some air movement away from that.
Really quick before I end the segment, you want to just show me the shop real quick?
Absolutely.
And then
here we have some of the magnetizing equipment for the power supply for this magnetizer, which we use for these small segments. We can also adapt it for the larger stator ring with different tooling to adapt it to focus on the magnetic cores.
how many watts or volts is this thing putting out?
Watts, it's a total about, I counted about 112,000, 118,000. Each one of these,
nice.
Each one of these is about 7,500 watts. And there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 12, 13 in there. And there's 14, 15 over there.
That's an awesome.
It's a lot. But in order to magnetize the larger stator rings, we would need this times 10. You need a megawatt, over a megawatt.
Now, what you said was very interesting earlier, that it's not necessarily a capacitive discharge, it's more of a slow imprinting.
Exactly. There is no capacitive discharge with this. Everybody else hammers the metal to make a magnet, and indeed it makes a north and south. But it's a very sloppy, very violent process. And what this is, you have to fine tune it and finesse it. It's like making a tuning fork.
Now I see why you would need liquid cores, because you're putting that kind of energy.
It's
against
not
each other.
capacitive discharge, so you have to. But again, you're turning the magnetizer on and off too during the process, which puts a lot of strain on it also.
Okay.
And you have to have three-phase power, which prevents the system from blacking out the whole district every time you go to magnetize a little layer.
I understand. Okay. And so this area over here, you said earlier, was just...
Yeah, don't get this guy right now.
Okay.
Sorry. But you know, we got some high-end equipment, so we can measure it out to precision, because this machine is made according to density. A lot of people, you know, CNC things according to length, width, height, or thickness, diameter, and thickness. This isn't like that. You can't just 3D print something like
We're
that.
on the same page there. Every time that I build circuits, one of the things is the density of the circuit is most important.
That's the whole key here. Well, in addition to the magnetization, which is the heart of it, without the density, you're not going to get it right, which is explained by his mathematics of the law of the squares, which I can give you a little rundown of why it takes the specific weights.
Really quickly, one time I needed to just get 2 potentiometers, and I went down to Fry's Electronics, and I measured on the scale some Chinese ones. None of them weighed the same. I'm like, that didn't make sense. The ones from Industrial Rectifier here in the USA, each one weighed exactly the same.
Yeah, but we got a lot of used Chinese equipment, and it's not exactly the
no, it's garbage.
These ones, they're measured to the hundredths of a thousandth of a gram, so 4 or 5 zeros past the decimal point. It's very accurate. If you put your hand in here, the radiant heat from your hand will affect the scale. It's
nice.
Really sensitive.
Nice.
Let's see what else. Yeah, we got this magnetizer that Fernando made a long time ago, connected with about 12 car batteries in series, which then proved that you can indeed imprint a waveform onto a magnetic material or a ferrite ring like this. And that's what the oscilloscope and Gauss meter probe showed, was that variation on there. What I did not show you is a comparison between a regular magnet and that one on that scope. If you put a regular one on there, it'd just be a flat line.
Interesting.
Because the block wall is an even flat line separating north from south. But on his magnets, there's like a divot. And then there's sub-frequencies, there's sub-carriers on that. You can't induce it. It's like it has to be programmed into the material in order for that to happen. You can't just fake that.
As you're speaking, I have, as you can probably tell, my wheels are spinning very, very fast in this. So for this right now, I'm going to end this segment. I'm going to talk to you off camera, but thanks, Jason.
Yeah, we have a lot more. Got a lot more, guys.
All right, cheers.